We all live our lives by a simple, quiet assumption that right now is the same now for everyone. That this very moment is a single, shared experience, a universal clock ticking in perfect unison for a person in Tokyo, a person in Toronto, and an astronaut floating high above us. It's the invisible bedrock of our reality, the shared stage where all our lives play out. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if I told you that physics says that's an illusion? A convincing one, sure. One our brains are hardwired to believe. But an illusion, nonetheless. What if your present is just your lonely slice of a vast, four-dimensional block of spacetime? A block where the reign of dinosaurs and the ultimate fate of our galaxy might already coexist. This isn't science fiction. It's arguably the most logical, and most unsettling, conclusion from our best theory of reality. It suggests that time doesn't flow, it just is. And that your now and my now might be fundamentally different. Today, we're pulling back the curtain on time itself. We're going to explore one of the deepest secrets of the cosmos. Why your now isn't the same as mine, and why the past, present, and future might all exist, side by side, all at once. We're going to decode the physics of time and find out exactly why the universe never agreed on now. It's a journey that will challenge your deepest intuitions and change how you see every single moment of your life. Before we smash this illusion to bits, let's take a second to appreciate just how powerful it is. Our feeling of a shared, universal now isn't just some casual hunch. It's practically hardwired into our brains and our entire civilization. It feels so real because, on a practical level, our brains and our societies are built on it. Think about what it feels like to be you, right now. You're experiencing this sentence at a specific moment. Light from your screen is hitting your eyes, maybe sounds are entering your ears. Your brain, this incredible biological machine, is gathering all those different signals and stitching them together into one seamless, coherent experience. It creates a little bubble of the present that feels about 3 seconds long. That's your psychological present. And the brain does this so well that we almost never notice the incredible work it's doing behind the scenes. For example, if you stub your toe, that pain signal has to travel all the way up to your brain. It takes a few dozen milliseconds. The light from you seeing your toe get stubbed reaches your brain much, much faster. But you don't experience these as two separate events. Your brain cleverly waits for all the info to arrive, then basically edits reality, creating a story of now, where the sight, the feeling, and the sound all happen together. Your brain is a natural-born storyteller, and its favorite story is the present moment. So from the get-go, our sense of now is a construction. This construction is incredibly useful for survival. For our ancestors on the savannah, matching the sound of a snapping twig with the sight of a predator was literally a life or death calculation. Our brains didn't evolve to be perfect physicists. They evolved to be kick-ass survival machines in a world where things move pretty slowly compared to the cosmic speed limit. As our societies got more complex, we started building external clocks. We made sundials, water clocks, hourglasses. We made calendars. But the true globalization of now really took off with trains. To stop trains from smashing into each other, railway companies had to sync their schedules. This led to standardized time zones, an invisible grid draped across the planet, declaring that now in London was officially different from now in New York. But for everyone inside New York, now was the same. Today, we live in the ultimate version of this shared time. GPS satellites carry hyper-accurate atomic clocks, all synced up to within nanoseconds of each other. The internet, the stock market, global news, It all runs on this basic assumption that we can all agree on the exact time. We've built a global civilization on this quiet, unchallenged faith in a universal now. It's the silent conductor of our global orchestra. And yet, for over a century, physics has been screaming at us that this conductor doesn't exist. The grand clock we all thought we were marching to is a ghost. The now that feels so absolute and so shared is, in the grand scheme of things, the most personal and private experience you can possibly have. To see how this solid foundation of a universal now starts to crumble, we have to go back to the late 1800s. Physics was feeling pretty good about itself. Isaac Newton's laws ruled. His universe was a predictable, clockwork machine. Space was a fixed stage, and time was a powerful river, flowing at the same rate for everyone, everywhere. In Newton's universe, now was simple. It was universal. An event happening on Earth right now was also happening, now, on Mars, and, now, in a distant galaxy. A single cosmic clock, ticking for everyone. But a storm was brewing. It started with the work of James Clerk Maxwell, a Scottish physicist who figured out how electricity and magnetism were connected. His elegant equations described how these forces work, and they made a wild prediction: the existence of electromagnetic waves that traveled at a very specific speed, about 300,000 kilometers per second. The speed of light. And here was the problem. Maxwell's equations said this speed was a constant. It didn't say what this speed was relative to. Which is just weird. Think about literally anything else that moves. If you're in a car going 100 kilometers an hour and you throw a baseball forward at 50, someone on the side of the road would see the ball moving at 150. Speeds add up. That's Newton's world. That's our world. But Maxwell's equations suggested light doesn't play by those rules. Whether you're standing still, on a train, or on a rocket ship, if you turned on a flashlight, that beam of light would race away from you at the exact same speed. This was a head-on collision with centuries of physics and common sense. It was a crack in the foundation of Newton's perfect clockwork universe. Physicists at the time scrambled to fix this. They even invented a mysterious, invisible substance called the luminiferous ether, a fixed medium that they thought filled all of space, that light must travel through. This would save Newton, but every single experiment designed to find this ether, to detect our motion through it, failed. The speed of light was stubbornly, infuriatingly constant for every person who measured it. The crisis was real. On one side, Newton's laws, which had worked perfectly for centuries. On the other, Maxwell's equations, which also worked perfectly. They couldn't both be completely right. Something had to break. Then, in 1905, a young patent clerk in Bern, Switzerland named Albert Einstein published a paper that changed history. He suggested something radical. He said, let's just stop looking for the ether. Let's just trust what the experiments are telling us. Let's assume two things are true. First, the laws of physics are the same for everyone. Second, the speed of light is the same for everyone, no matter how they're moving. Einstein decided to trust the weirdness of light. And by doing that, he was forced to throw out something far more fundamental: Newton's absolute, universal time. He realized that for the speed of light to be constant for everyone, space and time themselves must be flexible. They have to stretch and shrink depending on how you're moving. And from that simple idea, the entire concept of a shared now was about to unravel. Einstein's big idea had some breathtaking consequences, and the first casualty was the idea of simultaneity. The simple notion that two things can happen at the same time is the very definition of a now. If we can't agree on what's happening at the same time, we can't have a shared present. And Einstein showed, with a brilliantly simple thought experiment, that we can't. To really get this, we need to walk through this experiment step by step. It doesn't need any crazy math, just a promise to stick to one unbreakable rule. The speed of light is the same for everyone. So, imagine a long, straight railway track. Standing on a platform right in the middle is our first observer. We'll call him Albert. In the distance, a super-fast train is approaching. On that train, sitting exactly in the middle of a carriage, is our second observer. We'll call her Emmy. Now, for the action. At the exact moment the middle of Emmy's train passes Albert on the platform, two massive lightning bolts strike the track simultaneously. One hits the very front of Emmy's carriage, and the other hits the very back. Okay, let's see this from Albert's point of view. He's standing still on the platform, and he's the same distance from both lightning strikes. The light from the front strike and the light from the back strike travel towards him. Since he's in the middle, and both flashes travel at the exact same speed, they arrive at his eyes at the exact same moment. He sees two flashes at once. So, Albert gets out his notepad and writes, correctly from his point of view, that the two lightning strikes were simultaneous. They happened in his now. But what does Emmy see? This is where reality starts to bend. From Emmy's perspective, she's the one who's sitting still. The train carriage is her world. It's Albert and the platform that are whizzing past. That's the first rule of relativity. Her point of view is just as valid as Albert's. Now, let's think about the light from those two strikes. For her, just like for Albert, the light from both strikes travels at the constant speed of light. But Emmy is on a moving train. The lightning that hit the asterisk back of the train sent a pulse of light racing towards her. But she is moving towards that pulse of light. The train is carrying her to meet it. Meanwhile, the lightning that hit the asterisk front of the train also sent a pulse of light towards her. But she is moving away from that pulse. The light has to chase her down. Even though both light pulses travel at the same speed relative to Emmy, the light from the back of the train has a shorter distance to cover to reach her eyes. The light from the front has a longer distance to cover because it's chasing her. The unavoidable result? The flash from the back of the train reaches Emmy's eyes before the flash from the front. She sees the back strike, there's a pause, and then she sees the front strike. She gets out her own notepad and writes, correctly from her point of view, that the events were not simultaneous. The back of the train got hit first. So, who's right? Albert, who saw them happen at the same time? Or Emmy, who saw them happen one after the other? And this is where Einstein drops the bombshell. They're both right. There is no absolute, correct answer. There's no privileged observer. Simultaneity is relative. Whether two distant events happen at the same time depends entirely on how you're moving. This isn't a trick. It's not a delay in your brain. It's a fundamental feature of reality. The concept of now stretched across space isn't a property of the universe. It's a property of you. Albert has his now, a slice of time where both lightning strikes exist. Emmy has a completely different now, a tilted slice of time where one strike is in the past and the other is still in the present. The second you and I start moving relative to each other, our nows begin to tilt apart. We stop sharing the same present. And the faster we move, the more our nows disagree. Newton's universal clock is smashed. All that's left are countless, personal clocks, all ticking to their own relative beat. Okay, so if we can't even agree on what's happening now, what does that do to the past and the future? Well, following this logic leads you to one of the most mind-melting ideas in all of science, the block universe. Let's go back to Albert and Emmy. For Albert, both lightning strikes happen in his present moment. But for Emmy, the back strike happens first, and the front strike happens later. That means that at the moment Emmy is experiencing the back strike as now, the front strike, for her, is still in the future. But for Albert, at that same instant, both strikes are now. Think about what that means. An event that is in Emmy's future, the front lightning strike, is in Albert's present. This suggests the future isn't some foggy, unwritten void. It's a place that can be somebody else's now. This is the core idea of the block universe, sometimes called eternalism. It suggests that the divisions we make between past, present, and future are just a stubborn illusion of our perception. The most logical way to make sense of the relativity of simultaneity is to accept that all of time, every moment from the Big Bang to the very end of the universe, is equally real and coexists. The classic way to picture this is to imagine space-time as a giant, four-dimensional loaf of bread. Three dimensions are space, length, width, height. The fourth dimension is time. This entire loaf, this spacetime block, contains every single event that has ever happened or ever will happen. The birth of the Earth is a slice near one end. The age of dinosaurs is a bunch of slices further down. Your birth is a slice. You listening to this sentence is another slice. The last star in the universe flickering out is a slice way down at the other end. In this model, time doesn't flow. The loaf isn't being baked, it's already done. It just is. That feeling we have of time passing is just our consciousness experiencing one slice of this block after another. Our present is simply the slice we're on right now. Our past is just the stack of slices we've already been through, and our future is the stack of slices we haven't gotten to yet. This view, which Einstein himself grew to prefer, treats time a lot like we treat space. When you're standing in your kitchen, you don't think your living room has stopped existing or that your bedroom hasn't been created yet. You know they're all there, just in different places. The block universe says time is the same way. The year 1888 is just as real as this year, it's just in a different spot in time. The year 2288 is also just as real, we just haven't gotten there yet. Back on the train, Albert's slice of now cuts straight across the spacetime loaf, and on his slice, both lightning strikes appear. But Emmy, because she's moving, is taking a *tilted slice through the loaf. Her slice hits the timeline of the back of the train at an earlier point in the loaf's time dimension, and it hits the front of the train at a later point. Both slices are equally valid ways of cutting the loaf. They just show you a different cross-section of reality. The staggering implication is that events we consider to be in our future already exist on the now slices of observers moving very fast relative to us. An alien in a spaceship in the Andromeda Galaxy, traveling at just the right speed, could have a plane of simultaneity there, now, that slices through Earth in our year 2500. For them, our future is their present. By the same logic, another alien going the other way could have a now that slices through Earth during the Roman Empire. Our past is their present. This isn't just a quirky brain teaser. This is the world that Einstein's relativity describes. It forces us to wonder if our entire perception of time as a flowing river is just a trick of the mind. That in reality, the whole universe, in its four-dimensional glory, might just be a static, frozen block. A crystal universe where everything that will ever happen already is. Okay, trying to live with the idea of a block universe can be a little unsettling. It digs into the deepest questions about who we are and makes us look again at things we take for granted, like choice, memory, and the meaning of our lives. If the future is already out there, in the block, just as real as the past, what does that mean for free will? This is probably the biggest and most personal question people have about eternalism. If your entire life is already laid out as a fixed pattern in space-time, are your choices just an illusion? When you're agonizing over a big decision, what job to take, who to marry, what to have for breakfast, are you actually choosing? Or are you just an actor playing out a script that's already been written? The purely deterministic view of the block universe says, yeah, pretty much. In this view, your feeling of choosing is real, but the outcome was always set. Your brain is a physical thing, and it follows the laws of physics. The state of your brain cells before a choice leads, cause and effect, to the state of your brain cells after the choice. That whole chain of events is already part of the static geometry of spacetime. You aren't deciding your future, you're just discovering it as you go. But not everyone sees it that way. Some philosophers, called compatibilists, think free will and the block universe can actually get along just fine. They argue we just need to be more careful about how we define free will. Maybe it's not about the power to change a fixed future, but about being the asterisk reason your path through that future is the way it is. Think of it like this. The future where you choose the salad is a different future than the one where you choose the burger. Both might exist as fixed paths in the block, but it was your thoughts, your character, your desires, the whole complex machine of you, that determined which path your life took. Even if the outcome is fixed, the fixing happened through you. Your choices are still meaningful because they are the link that connects your past to your future. If you were a different person, your path through the block would have been different. The block universe also changes how we think about the past and future. Our relationship with the past becomes more intimate. Memories aren't just faint ghosts of moments that are gone forever. In a block universe, the moments we cherish aren't destroyed by time. They are permanent parts of reality, existing in their own time and place just as surely as this moment exists now. They are still there, in the block, eternally preserved. The past isn't lost, it's just in a different place. And the future? It's not an empty void, but a solid landscape we just haven't explored yet. This doesn't mean we can know the future. The laws of physics, especially quantum mechanics and chaos theory, would probably stop anyone from ever gathering enough data to predict their path with certainty. The book may be written, but we're forced, or blessed, to read it one line at a time, without ever skipping to the end. And what about time travel? The block universe makes traveling to the past seem, at least in theory, more like traveling to a different location in space. But it also neatly solves a lot of the paradoxes. For instance, the grandfather paradox. What if you go back and stop your grandparents from meeting? In a static block universe, you can't change the past. If you travel to the past, your trip and everything you do there was already part of the block. You wouldn't be changing history, you'd be fulfilling it. The loaf is already baked, you can't unbake a slice. But for all its logical beauty, the block universe isn't the final word. Because physics has a split personality. On one hand, you have Einstein's relativity, which gives us this beautiful, static, geometric universe. On the other hand, you have quantum mechanics, and it gives us something much, much weirder. General relativity describes the big stuff, planets, galaxies, the smooth fabric of spacetime. Quantum mechanics describes the tiny stuff, particles, probabilities, and uncertainty. And when it comes to time, the two theories really don't agree. The most obvious clash is the arrow of time. In our lives, time clearly has a direction. Eggs break, they don't unbreak. Ice cubes melt, they don't spontaneously freeze themselves back into cubes. This is the second law of thermodynamics. The idea that disorder, or entropy, always tends to increase. This law gives time a clear, forward-pointing arrow. But the static block universe doesn't really have an arrow. In its geometry, forward and backward in time are no more special than left and right in space. So why do we only experience it one way? It's one of the biggest mysteries in physics. On top of that, quantum mechanics brings a fundamental randomness to the table that just doesn't sit right with the deterministic feel of the block universe. According to quantum mechanics, the future seems genuinely open and based on probabilities, not a fixed landscape. This has led to other ideas about time. Some physicists, like Carlo Rovelli, argue that time isn't fundamental at all. It might just be an emergent thing that pops up from the quantum interactions between stuff. In this view, time is just a way of measuring change. Other theories try to mix the block universe with quantum weirdness. The many worlds idea suggests that every time a quantum event with multiple possible outcomes happens, the universe splits. In that case, the block universe isn't one loaf of bread, but an infinitely branching tree of loaves. where every single possibility plays out in its own parallel universe. So, which is it? Is the block universe a solid crystal, with the future set in stone? Or is it more like a block of fog, where the future is just a haze of possibilities until we actually live it? The honest answer? We don't know. The conflict between general relativity and quantum mechanics, the hunt for a theory of everything, is the single biggest problem in physics today. Figuring out what time really is probably has to wait until we solve that. The block universe is the story that relativity tells us. Quantum mechanics is telling a different one. The full story isn't finished yet. This whole journey into time shows just how much we still have to figure out about reality itself. The block universe is a powerful idea, a logical result of our best theory of gravity, but the questions it raises are a long way from being settled. So what do you think? Is our feeling of flowing time just a profound illusion, and we're all just exploring a static, 4D block? Or does the quantum world guarantee that our future is truly unwritten? I'd love to hear your thoughts in the comments. And if you enjoy wrestling with these kinds of huge, cosmic questions, make sure to subscribe and hit that notification bell so you don't miss our next trip into the wild secrets of the universe. We started with a simple, comfortable idea. That now is a moment we all share. We traveled back to a crisis in physics, where the stubbornness of light forced a young Albert Einstein to tear down our most basic ideas about reality. We walked through his thought experiment and watched as the solid ground of a universal present dissolved into countless, personal, nows. This led us to the staggering idea of the block universe, a 4D spacetime where past, present, and future all exist, equally real. A universe that isn't happening, but that simply is. We looked at what that means for fate, free will, and our own lives, and we saw how the weirdness of the quantum world adds a deep, unresolved wrinkle to the whole picture. So where does that leave us? It leaves us right here. In this moment, your moment. It might not be a universal, now, that's shared with everyone across the cosmos. It might just be your own, private, lonely slice of this giant cosmic loaf. But the incredible thing is that you get to experience it. Your consciousness, for a brief flicker in the grand timeline of the block, is the light that's illuminating your slice. The flow of time might be an illusion, but the asterisk experience of that flow, the experience of life, of love, of joy, is undeniably real for you. And maybe that's the ultimate truth of our universe. This strange, beautiful paradox, that we live inside a frozen, timeless reality, but we experience it as a dynamic, unfolding story. We are both characters with a pre-written destiny and the readers turning the page for the very first time. Your now may not be the universe's now, but it is, and always will be, yours. There is a sense that the now you're experiencing is shared. That a single, universal moment is unfolding for everyone, everywhere. But this idea, as comfortable as it is, may not be a fundamental feature of the universe. It might only be a feature of our perception. Consider a long, straight railway track. An impossibly fast train moves past. At the exact moment the middle of the train is in front of an observer on the ground, two bolts of lightning strike the train. One hits the very front, the other hits the very back. From the ground, the two flashes appear to happen at precisely the same time. They seem, in every way, simultaneous. And yet, for a passenger sitting in the exact middle of that train, they were not. She would report, with equal certainty, that one bolt struck before the other. So, who is right? The observer on the ground, or the passenger on the train? The answer is not a riddle. It is a quiet instruction on the nature of reality. It suggests that the universe is a more personal, and more relative, place than our senses tell us. In this disagreement lies a deep truth. The universe does not have a single, agreed-upon, now. To understand this contradiction, we must set aside our everyday intuition. Our feelings about space and time are shaped by a world of slow movement. To see the universe as it is, we have to play by its rules. A little over a century ago, those rules were clarified by Albert Einstein. In 1905, he published his special theory of relativity. Its vast consequences all grow from two simple statements or postulates. To resolve the matter of the two lightning strikes, we need to understand these two rules. They are the framework for the problem. The first is the principle of relativity. It is an idea you experience often. On a smooth flight, moving at a constant 800 kilometers per hour, the world inside the cabin feels normal. A tossed peanut goes up and comes straight down. Walking the aisle feels no different than walking at home. If the window shades were closed, no experiment you could perform inside would prove you were moving. This is the first postulate. The laws of physics are the same for all observers in uniform motion. This idea dates back to Galileo. He imagined a cabin on a smoothly sailing ship, where fish in a bowl and dripping water would behave just as they do on land. There is no absolute state of rest. Motion is only meaningful relative to something else. A passenger on the plane sees the peanut as still, relative to their hand. An observer on the ground sees it tracing a wide arc across the sky. Both viewpoints are valid frames of reference. The laws of physics work perfectly in both. Our observer on the ground, we can call her Stacy, is in one frame. The passenger on the train, Mo, is in another. According to the first rule, neither perspective is more correct. The second rule is where our familiar reality begins to feel distant. It is the principle of the constancy of the speed of light. It states that the speed of light in a vacuum, a cosmic limit of about 299,792 kilometers per second, is the same for every observer. It does not matter how the observer is moving, or how the source of the light is moving. This idea sits uncomfortably with our sense of the world. If a car moves towards you at 100 kilometers per hour and the driver throws a ball forward at 50, you perceive the ball's speed as 150 kilometers per hour. The speeds add together. It is common sense. But if a spaceship flies toward you at half the speed of light and turns on its headlights, that logic fails. The light from those headlights will approach you at exactly the speed of light, not 1.5 times the speed of light. If the spaceship flies away from you, the light still approaches you at the speed of light. This is not a theory, but one of the most tested facts in physics, growing from the work of James Clerk Maxwell and the famous Michelson-Morley experiment, which tried and failed to detect a change in light speed. Einstein accepted this strange failure not as a puzzle to be solved, but as a fundamental truth. Light is not like a ball. Its speed is woven into the fabric of reality. These are the two rules. First, the laws of physics are universal for all non-accelerating observers. Second, the speed of light is constant for all observers. Together, they lead to a conclusion about time that is as unavoidable as it is unfamiliar. With these two principles, we can return to the train and understand what each person saw. We begin on the solid ground of the railway embankment, with Stacy. She is positioned at the exact midpoint between the two locations on the track where the lightning will strike. She is our stationary observer. The train moves past. Just as its center aligns with her, it happens. A flash of light to her left, and an identical flash to her right. Let us call the strike at the back of the train event A, and the strike at the front event B. From Stacy's perspective, she is certain they occurred at the same time. But a physicist relies on measurement. The definition of simultaneity for two distant events is precise. An observer can say they happened at the same time if light from those events reaches them at the same time, provided they know they are at the exact midpoint between the events. Let's follow the light. When lightning strikes at event A, the light begins to travel along the track toward Stacy. When lightning strikes at event B, its light does the same. Here, we must use Einstein's second rule. The light from event A travels toward Stacy at speed c. The light from event B also travels toward Stacy at speed c. and Stacy is not moving. Because she is at the exact midpoint, the distance from the char mark at A to her eyes is identical to the distance from the char mark at B. So we have two signals of light. Both travel at the same constant speed. Both cover the same distance. Because distance equals speed multiplied by time, the time of their journeys must also be the same. The light from both strikes will arrive at her eyes at the same instant. For Stacy, the observation is clear. She was at the midpoint. She received the signals at the same time. Her conclusion is supported by the rules of physics. Event A and event B were simultaneous. From her frame of reference, now, contained both flashes. For a moment, common sense seems to hold. But we have only heard one side of the story. Now, we must step onto the moving train, and into a different reality. Now, we shift perspective to the train, with our second observer, Mo. He sits in a seat in the exact center of the train, equidistant from its front and back. From his point of view, he is sitting still. The world outside is a blur, but his frame of reference is calm. According to Einstein's first rule, his perspective is just as valid as Stacy's on the ground. The laws of physics must work for him in the same way. From the ground, we know the lightning strikes the track and train simultaneously. A char mark is left at the front of the train, and one at the back. Light from these two events begins to travel. This is where the perspectives diverge. Remember, Mo is on a train moving forward. The light from the front of the train, event B, begins traveling back toward him. But Mo is moving towards that incoming pulse of light. He is rushing to meet it. Meanwhile, the light from the rear of the train, event A, travels forward toward him. But Mo is moving away from that incoming pulse. The light from the back is chasing a receding target. Now we must return to Mo's frame of reference, where he feels perfectly still. And we must remember the second, crucial rule. For Mo, the speed of the light from both the front and the back is still exactly c. The speed of light does not change. What has changed is the distance the light must travel to reach his eyes. Because he is moving toward the location of the front strike, the light from event B has a shorter distance to cover. And because he is moving away from the location of the rear strike, the light from event A has a longer distance to cover. This is what happens for Mo. Two signals of light, both traveling at the same constant speed relative to him. But one has a shorter journey, and the other has a longer one. It is a physical certainty that the light from the front of the train, event B, will reach his eyes before the light from the back of the train, event A. So, what does Mo conclude? He is an equally valid observer. He knows he is in the middle of his train. He performs the same measurement as Stacy. First, he sees the flash from the front. A moment later, he sees the flash from the back. His conclusion, based on the same laws of physics, is just as logical and just as inescapable. The events were not simultaneous. For Mo, the lightning struck the front of the train first. This is the quiet contradiction. Two observers, both using the correct laws of physics, have arrived at opposite conclusions. Stacy says A and B happened at the same time. Mo says B happened before A. Who is right? So, who is correct? Stacy, on the ground? Or Mo, on the train? It seems they cannot both be. And yet, the answer confirmed by a century of physics is that they are. They are both right. Stacy is right in her frame of reference. Mo is right in his. The contradiction resolves when we are forced to set aside one of our deepest assumptions: the belief in absolute simultaneity. Einstein's theory reveals that there is no universal, now, that everyone agrees on. The concept of two events happening, at the same time, is not a property of the events themselves. It is a relationship between those events and a specific observer. This is the idea known as the relativity of simultaneity. What this means is that simultaneity is in the eye of the beholder. For Stacy, her slice of now contained both lightning strikes. For Mo, the moment the front flash arrived was his now, and that moment did not include the rear flash. For him, that event was still in the future. When the rear flash did arrive, the front flash was already in his past. Reality is not a single film that everyone watches together. It is more like a library of films, each showing the complete history of the universe from a different perspective. Stacy can pause her film on the exact frame where both flashes appear. But Mo is watching a different cut. On his film, the frame showing the front flash comes before the frame showing the rear flash. Both films contain the same events, but their timing is different. And neither film is the correct version. They are all equally valid. This asks us to reconsider the idea of time as a great river flowing at the same rate for everyone. It is more like a complex delta of countless streams, each one representing a possible frame of reference. My now is a cross-section of my stream. Your now is a cross-section of yours. If we are moving relative to one another, our cross-sections will slice through the block of universal events at different angles. This is not an illusion of perception. It is not about the time it takes for information to reach us. Both Stacy and Mo correctly account for the travel time of light in their own frames. The difference is real. Time itself is shaped by motion. The present moment is not universal. It is personal. Accepting that now is relative has profound consequences. It quietly reshapes our picture of time and reality. Perhaps the most startling implication is an idea known as the block universe. If there is no universal now, if one observer's present can be in another's past, and a third observer's future, then the distinction between past, present, and future seems to become less rigid. This leads to a picture where all of time, every moment that has happened and will happen, exists and is equally real. Think of spacetime as a loaf of bread. Our common sense view is that only one slice, the present, is real. The past is gone, and the future is not yet formed. But the relativity of simultaneity suggests this is not so. If different observers have their own valid slice of now, and these slices are angled differently, then for all of them to be real, the entire loaf must also be real. The past is not gone. The future is not unwritten. It is all simply there. In this view, our feeling of time flowing is an illusion of consciousness, our awareness moving through the existing frames. This led Einstein to write, for as physicists, the distinction between past, present, and future is only an illusion, however persistent. This might seem to invite chaos. Could an effect be seen before its cause? The theory protects causality absolutely. If two events are close enough that a signal can travel between them, then all observers will agree on their order. The lightning must strike before the light can reach Mo's eyes. The order of causally connected events is absolute. The relativity of simultaneity only applies to events that are space-like separated, so far apart in space that light does not have time to travel between them. Only for these causally disconnected events can observers disagree on the order. The universe is strange, but it is not illogical. And this is not just theory. The effect is essential for technology you use every day. The Global Positioning System, or GPS. Your phone finds your location by receiving signals from satellites orbiting the Earth at high speeds. These satellites carry precise atomic clocks. For GPS to work, all these clocks must be synchronized. But because of the relativity of simultaneity, clocks synchronized on the ground will appear unsynchronized from the moving satellite's frame. Engineers must pre-correct the satellite clocks to account for this. Without these corrections for relativity, GPS navigation errors would grow by about 12 kilometers every day. The fact that you can find your location on a map is quiet, daily proof that now is relative. The absence of a universal now extends to the entire cosmos. It changes how we can think about the universe beyond our own local neighborhood. Ask a simple question. What is happening in the Andromeda galaxy right now? Our intuition suggests that 2.5 million light-years away, an alien astronomer might be looking at their sky, sharing this very instant with us. But special relativity tells us the question itself is based on a flawed assumption. When we look at Andromeda, we see it as it was 2.5 million years ago. That is how long its light took to reach us. By the same token, an observer in Andromeda would see Earth as it was 2.5 million years ago, a world of early hominids. The relativity of simultaneity makes this even more profound. An observer on a planet in Andromeda, flying in a spaceship at high velocity away from us, would have their plane of simultaneity, their slice of now, angled differently through spacetime. Their now might correspond to what we consider the year 1888 on Earth. To them, at this moment, the Eiffel Tower is under construction. Another observer in Andromeda, flying at high velocity towards us, would have their plane of simultaneity angled the other way. Their now could correspond to what we would call the year 3000. To them, humanity may have already explored the stars. Both perspectives are completely valid. There is no cosmic referee to declare one of them the true present. This means our past, our present, and our future can all exist as a valid present moment for different observers elsewhere in the universe. This forces us to abandon the image of the universe as a single entity evolving together. There is no master clock. The universe is a vast, four-dimensional tapestry of events, and each of us traces a unique path through it. There is no now for the universe. There is only the here and now for you. This is a humbling realization. Our sense of a shared present is a local phenomenon, born from a life lived at slow speeds in a small corner of the cosmos. The universe does not have a single story. It has a near infinity of them, all being told at once. We began with a simple observation, 2 lightning strikes and a speeding train. We end by reconsidering the nature of time itself. By following the quiet, rigid rules of physics, we arrive at a staggering conclusion. The idea of a universal now is an illusion. We saw how 2 observers, both logical, both obeying the same physical laws, can experience a different sequence of events. Stacy on the ground and Mo on the train were both right. Their realities were simply different. This is not a trick of the mind, it is a fundamental feature of the spacetime we inhabit. We have seen this strange property as not just theory, but a practical reality that makes our technology work. And on the largest scales, it dissolves the notion of a shared cosmic present, leaving a universe where past, present, and future can all exist at once, depending on the observer. Our common sense feeling of a single river of time is a product of our environment. We live at speeds that are barely a crawl on the cosmic scale. In our world, disagreements about now are too small to notice. But the universe operates on rules that are more strange and elegant than our senses reveal. Time is not a ticking clock on the wall of the cosmos. It is a dynamic and malleable entity, woven into the fabric of space, and it unfolds to a different rhythm for each of us. If this kind of calm exploration into the nature of reality helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a forest, or somewhere quiet in between, feel free to share what concept in physics you would like to see untangled next. There is a feeling we all share, so fundamental it often goes unnoticed. The feeling of now. Right now, you are watching this video. Right now, somewhere in a distant nebula, a star is forming. Right now, on the other side of the planet, a city is waking. We live our lives in this shared moment, a universal present that seems to connect every part of the cosmos in a single, silent tick. The past is a memory, the future is an idea, but the present feels real. But what if this shared, universal now is an illusion, a subtle artifact of our perception? What if every movement you make, even walking across a room, gently reshapes this present moment, creating a now that is exclusively yours? This is not speculation. It is a quiet reality of the universe, revealed by one of the most careful thinkers in human history. The idea that we all share a single now is perhaps the most intuitive, and the most incorrect, assumption we make about our world. Today, we will explore why, according to physics, there is no single now for the entire universe. We will journey from the clockwork certainty of an older world to the unfamiliar reality of the new, and by the end, our understanding of time itself may feel very different. For most of human history, our idea of time was simple and intuitive. Time was like a great river, flowing at the same steady pace for everyone, everywhere. A second on Earth was a second on Mars, and a second in the most distant galaxy. This idea was so obvious it hardly needed to be stated. It was the foundation of perception, the silent metronome marking the unfolding of all events. This intuitive notion was given a formal, scientific seal of approval by Sir Isaac Newton. In his Principia Mathematica, Newton defined what he called absolute, true, and mathematical time. He described it as something that, of itself, and from its own nature, flows equably without relation to anything external. For Newton, time was an outsider. It was a single, universal clock, ticking with perfect regularity, completely independent of space, of matter, of motion. It was the stage upon which the universe performed, but it was not an actor on that stage. In Newton's universe, the concept of now was absolute. If an event happened in the Andromeda galaxy at the same moment a bell rang in London, those two events were simultaneous for every observer in the cosmos. This created a clean, orderly reality. The universe had a definitive, shared present. All of existence could be sliced into a stack of nows, like pages in a book, each page a single, frozen instant across all of space. This view worked perfectly for over 2 centuries. It was the foundation of classical physics, allowing us to predict the motion of planets and build our world with astonishing precision. There was no reason to doubt it. Time was time and space was space. The two were separate and absolute. It was a simple, elegant picture of reality. And it was about to be gently, but completely, taken apart by a young patent clerk in Bern, who was thinking about the nature of light. In 1905, Albert Einstein was working a quiet job, examining patent applications. But in his spare time, he was considering a subtle paradox at the heart of physics. The issue was not with time itself, but with light. In the late 19th century, physicists, guided by James Clerk Maxwell, had unified electricity and magnetism into a single theory. A remarkable prediction emerged from Maxwell's equations. Light was an electromagnetic wave that always traveled at a very specific speed in a vacuum, a value we call c. That speed is immense, about 300,000 kilometers per second. But the truly strange part was not its value, but its nature. The equations suggested that the speed of light was constant. This sounds simple, but its nature is profoundly unfamiliar. Imagine you are standing beside a road, and a car passes you at 50 kilometers per hour. Now, imagine you get in another car and drive at 30 kilometers per hour in the same direction. From your perspective, the first car is now moving away from you at only 20 kilometers per hour. Speeds add and subtract. This is our everyday, Newtonian experience. Now, let's replace the car with a beam of light. You are standing still, and you measure its speed. You get c. Now, you board a hypothetical rocket and travel at half the speed of light, 150,000 kilometers per second, in the same direction as the light beam. Common sense suggests that when you measure the speed of the light beam now, you should get c minus your own speed, or half of c. But you do not. You measure its speed, and you get c. Exactly. You turn your rocket around and fly in the opposite direction, away from the light source, at half the speed of light. Logic suggests the light should now appear to pass you at 1.5 times c. But again, when you measure it, its speed relative to you is still, impossibly, c. This is the first pillar of Einstein's work, the principle of the constancy of the speed of light. No matter how fast you move, or in what direction, a beam of light in a vacuum will always be measured to have the exact same speed. The second pillar was the principle of relativity. This idea, which goes back to Galileo, states that the laws of physics are the same for all observers in smooth, non-accelerating motion. There is no special, privileged, stationary place in the universe. Your motion is only ever relative to something else. Einstein considered these two principles together. He realized that for both to be true, something we thought was untouchable had to be flexible. That something was Newton's absolute time. If the speed of light refuses to change, then space and time themselves must stretch and shrink depending on your motion, to ensure every observer measures the same value for c. This was the quiet revolution. Space and time were not a static stage. They were active participants in the universe, woven into a unified fabric Einstein would later call spacetime. This weaving has two consequences that lead to the dismantling of a universal now. The first is known as time dilation. To understand how motion affects time, we can use one of Einstein's favorite tools, a thought experiment. This is the light clock. Imagine a simple clock made of two parallel mirrors, with a photon of light bouncing between them. Let's say it takes the photon exactly 1 second to travel from the bottom mirror to the top and back again. Each time the photon returns, the clock ticks. 1 second, 2 seconds. A simple, reliable clock. Now, we place this clock on a transparent train and set it in motion. You are standing still on the platform, watching it pass. From your perspective, what does the photon's journey look like? For someone on the train, the photon is still just going up and down. But for you on the platform, the train is moving. By the time the photon travels from the bottom mirror to the top mirror has moved to the right. And by the time it reflects back down, the bottom mirror has moved even further. From your point of view, the light does not travel in a straight line. It travels a longer, diagonal, zigzag path. This is the crucial point. The path the photon takes is undeniably longer from your perspective than from the perspective of someone on the train. Now, we remember Einstein's first principle. The speed of light is constant for all observers. Both you and the person on the train must measure that photon to be moving at speed, c. But speed is distance divided by time. If the speed, c, is the same for both of you, but the distance the photon travels is longer for you, there is only one possible conclusion. The time it takes for that journey must also be longer from your perspective. This means that from your stationary point of view, the moving clock's tick takes longer than 1 second. You see the moving clock ticking more slowly than an identical clock in your hand. This is not an illusion. The clock on the train is genuinely running slow from your point of view. Time itself, for everything on that train, is passing at a slower rate. This effect is called time dilation. Moving clocks run slow. It's not just clocks. All physical, chemical, and biological processes slow down. If a person on the train aged 1 year according to their own watch, you might measure that period as 2 years. From your perspective, they have aged more slowly. At everyday speeds, this stretching of time is almost zero, which is why we never notice it. But as an object approaches the speed of light, the effect becomes significant. This has been verified many times. Unstable particles called muons, which should decay in microseconds, survive much longer when traveling near the speed of light because their internal clocks are ticking slower from our perspective. The GPS system in your phone must account for this. Satellites orbit at high speed, so their atomic clocks tick slightly slower than clocks on the ground, by about 7 microseconds each day. If engineers did not correct for this, your GPS would become inaccurate by several kilometers every day. Time dilation is the first sign that absolute time does not exist. It shows that my second and your second are not always the same. But it is the other consequence of light's constant speed that fully dismantles the idea of a universal now. This is the relativity of simultaneity. This concept lies at the heart of our investigation. It is more subtle than time dilation, but its consequences are more profound. It means that two events that happen at the same time for one person can happen at different times for another. And both people are correct. This is the idea that removes the possibility of a shared, cosmic, now. Let's return to our train for a thought experiment first imagined by Einstein. Imagine a very long, fast train. In the exact center of this train is an observer, Anna. Standing on the ground, also at the midpoint of the tracks, is another observer, Bob. Just as Anna is passing directly in front of Bob, two bolts of lightning strike the train simultaneously. One hits the very front, the other hits the very back, leaving scorch marks on both the train and the tracks. Let's first consider Bob's perspective. He is on the ground, exactly halfway between the two scorch marks on the tracks. The light from the front strike and the light from the back strike travel toward him. Since he is in the middle and the speed of light is constant, the two flashes reach his eyes at the exact same moment. From this, Bob correctly concludes that the two lightning strikes were simultaneous. For him, they were part of the same now. Now, let's switch to Anna's perspective inside the moving train. She is also in the exact middle of her train. However, the train is moving forward. From Bob's point of view on the ground, Anna is moving towards the light flash coming from the front, and moving away from the light flash coming from the back. The light from the front strike has a shorter distance to travel to reach her. The light from the rear strike has a longer distance to travel, because it must catch up to her as she moves away. Since the speed of light is constant, and the distances the light must travel to reach Anna are different, the two flashes will not reach her at the same time. The light from the front bolt will reach her first. The light from the rear bolt will arrive a moment later. So what does Anna conclude? She is in the middle of the train. She sees a flash from the front, and then a moment later, a flash from the back. Her only logical conclusion is that the lightning must have struck the front of the train before it struck the back. The events were not simultaneous for her. Here we arrive at the quiet, unavoidable conclusion. For Bob, the two strikes happened at the same time. They were part of his now. For Anna, the front strike happened first. They were not part of the same now. Who is right? Both of them are. There is no absolute fact about whether the two events were simultaneous. Simultaneity is relative. It depends on your state of motion. This is what dissolves the idea of a universal now. If we cannot agree on whether two events in different places happened at the same time, then the concept of the same time across the universe becomes meaningless. Imagine your now as a flat, horizontal slice through the four-dimensional block of spacetime. This slice contains every event in the universe happening simultaneously for you. For someone standing still next to you, their slice of now is parallel to yours. You agree on what is happening now. But as soon as someone begins moving relative to you, their slice of now tilts. For Anna on the train, her now is tilted relative to Bob's. In the direction she is moving, her now slice is angled into Bob's future. In the direction opposite her motion, her slice is angled into Bob's past. This means an event that is in Bob's present at a great distance in front of the train is actually in Anna's past. And an event that is in Bob's present far behind the train is in Anna's future. The very notion of a universal present is a myth. There is no single sheet of now that covers the cosmos. Instead, there are countless, overlapping, and differently tilted nows, one for every possible state of motion. Your now is personal, defined by your specific path through spacetime. If there is no universal now, what does that suggest about the nature of time itself? The implications lead many physicists to a picture of reality known as the block universe. Think of spacetime. the four dimensions of space and time, as a single, static block. Imagine it as a loaf of bread. A slice of that loaf represents a moment in time. In the old Newtonian view, everyone agreed on how to slice the loaf. The slices were straight and parallel, each one a universal, now. But as we have seen, relativity shows there is no single, correct way to slice the loaf. One person's slice of now is tilted relative to another's. My now cuts across the block at a different angle than the now of an astronaut moving at high speed. If my now can contain an event that is in your future, it suggests something radical. That all moments, past, present, and future, are equally real. In the block universe model, the universe's entire history, from its beginning to its end, exists as a whole. The dinosaurs are not gone. They are simply in a different part of the spacetime block. Your birth, this moment right now, and the end of your life are all just different coordinates within this four-dimensional structure. The flow of time, that feeling of moving from a fixed past toward an open future, might be an emergent property of our consciousness. We are like a spotlight moving along the film reel of our lives. The entire movie already exists on the reel. Our consciousness simply illuminates one frame at a time, giving us the illusion of passage. Albert Einstein seemed to hold this view. After the death of his friend Michel Besso, he wrote to Besso's family, "Now he has departed from this strange world a little ahead of me." That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. This view is a stark departure from our intuition, which is known as presentism, the idea that only the present is real. Another view, the growing block universe, suggests the past and present exist, but the future does not, with now being the edge where reality is created. However, the relativity of simultaneity creates problems for these ideas. If my now can include part of your future, it becomes difficult to argue that the future does not exist in some form. For this reason, many physicists and philosophers find the block universe to be the most logical interpretation of what relativity tells us about reality. You might be thinking, this is fascinating, but it is all about fast trains and distant galaxies. Does the tilting of now have any real impact on my life? The answer is yes, every day. The most familiar example is the Global Positioning System, or GPS. Your phone's navigation system works by receiving signals from satellites, each with a precise atomic clock. To find your location, the system measures tiny differences in the arrival time of these signals. This requires timing accuracy down to billionths of a second. Here, we see two relativistic effects. First, time dilation. The GPS satellites move at about 14,000 kilometers per hour. Special relativity tells us this causes their clocks to run slower than clocks on the ground by about 7 microseconds every day. Second, there is an effect from Einstein's general relativity, which shows that gravity also warps time. Clocks in a weaker gravitational field tick faster. The satellites are far above Earth, where gravity is weaker, so this effect causes their clocks to run faster than ground clocks by about 45 microseconds per day. The net result is that the satellite clocks get ahead of Earth clocks by about 38 microseconds daily. This seems small, but if engineers did not build corrections for relativity into the GPS system, the errors would add up to over 10 kilometers per day. The system would be useless within minutes. The fact that your phone can guide you to a destination is quiet, daily proof that motion and gravity change the flow of time. Another example is the twin paradox. If one twin stays on Earth while the other travels to a distant star near the speed of light, the traveling twin will be younger upon return. This is a direct consequence of time dilation. Because the traveler accelerated and turned around, they changed reference frames, making the age difference real and measurable for both. So while we may not perceive our personal slice of now tilting as we walk down the street. The principles that cause it are woven into the technology we use and the fundamental rules of the cosmos. Your every movement, however slight, alters your relationship with the rest of the universe, creating a present moment that is uniquely yours. If this quiet exploration into the nature of time has helped you see the world differently, consider liking the video and subscribing to the channel for more journeys into science. We would be interested to hear your thoughts in the comments. Does the idea of a block universe, where the past and future are as real as the present, feel comforting or unsettling to you? We began with an intuitive feeling. The feeling of now, a universal moment we all seem to share. We saw how this idea was formalized by Newton into a single cosmic clock. But the quiet logic of Einstein, driven by the unchanging nature of light, required us to leave this comfort behind. We discovered that motion slows the passage of time. More profoundly, we learned that motion alters our very idea of what happens at the same time. The relativity of simultaneity shows us there is no single, agreed upon, now, for the universe. Each of us, based on our unique path through spacetime, carves out our own personal slice of the present. This leads us to the staggering picture of the block universe, a four-dimensional reality where past, present, and future may all exist together, and our experience of time's flow is a deeply personal, human phenomenon. The universal, now, is an illusion, but it is a powerful one. Our minds evolved to navigate a world where speeds are slow and these effects are unnoticeable. Our shared experience of the present is what connects us. But the universe, in its grandest structure, operates on different rules. It does not have a single moment called now. Instead, it is a vast tapestry of spacetime, where every event has its place, and now is simply a point of view. Reality is far stranger, and far more wonderful than we often imagine. There is an idea, a feeling, that the present moment is something we all share. We imagine time as a quiet current, moving all of us forward together, past the shores of what has been and toward what is not yet. But this feeling, this deep intuition of a single, universal, now, is something physics began to question more than a century ago. It is an idea that our experience holds onto, even when science suggests it may not be the entire story. There is no great cosmic clock, no single beat that the whole of existence follows. Physics reveals something quieter and stranger. It suggests that what you feel is now is, for someone else, a moment in their past. For another, that same moment might still be in their future. It is an idea that feels more at home in myth than in physics, yet it sits at the heart of our modern understanding of the universe. This is a journey into that idea, a calm exploration of why the universe never agreed on when now is. And by the end, our own relationship with time might feel a little different. Before we arrive at Einstein's unfamiliar universe, let us first spend a moment with the idea that feels so natural, the one that shapes our everyday. This is the world of classical time, the time of our own intuition. Imagine coordinating a single moment of silence across the entire planet. We send a message. Let us all be silent at exactly 12 p.m. Coordinated Universal Time. We picture it without effort. As a clock strikes noon in Greenwich, a wave of quiet spreads across the world. In Tokyo, where evening has already arrived, people fall silent. In New York, in the early morning, they pause. For a single, shared instant, a single, now, the world feels connected in quiet contemplation. This is the common sense view of time. The idea that it is absolute, flowing at the same rate for everyone, everywhere. Sir Isaac Newton built his mechanical universe on this foundation. For him, time was an absolute background, a silent cosmic metronome ticking uniformly for a planet orbiting a star and an apple falling from a tree. It was the unseen stage upon which the cosmos performed its silent play. Now, in London was the very same now, in the Andromeda galaxy, 2.5 million light-years away. This idea is powerful because it matches our own experience. When you speak to a friend on the phone thousands of miles away, you do not doubt that you both exist in the same present. You share a now. Our societies, our technologies, even our language are built upon this assumption of a single, all-encompassing present. We synchronize our watches and count down the seconds to a new year as if we are all tied to one unseen clock. And for almost every purpose in our lives, this model works. The differences are so small they remain invisible. One could live a whole life, build cities, and explore the earth without ever needing to question this idea. The passage of time for someone standing still and someone on the fastest train differs by only a tiny fraction of a second over a lifetime. It is an excellent approximation for the world we experience on a human scale. And yet, the universe is not only built to human scales. It also operates on scales of immense distance and speed. When we begin to venture there, the comfortable, intuitive idea of a universal now begins to dissolve. It doesn't simply become inaccurate, it reveals a reality that is far more quietly strange than Newton could have imagined. The central mystery we are going to explore is why this feeling of a universal now is such a profound illusion. And the key to understanding it, the key that revealed this new reality, was a single, simple idea about the nature of light. That key was held by Albert Einstein, and it didn't just challenge our concept of a shared now, it quietly replaced it. So let us leave the familiar world of Newton, and take a first step into the strange and beautiful world of relativity. In 1905, a young patent clerk named Albert Einstein offered a new way of seeing. His theory of special relativity was built on two deceptively simple ideas. Two rules he proposed were true for the entire universe. It is in the consequences of these two rules that our notion of a shared now gently unravels. Let's explore them, as they are the foundation for everything that follows. The first is the principle of relativity. It simply says that the laws of physics are the same for anyone moving at a constant speed in a straight line. There is no special, privileged state of rest in the universe. Imagine you are on a perfectly smooth train with no windows. If you drop a ball, it falls straight down, just as it would if you were standing still. There is no experiment you can do inside the train to prove you are moving. From your perspective, you are stationary, and the world outside is rushing past. This idea had been understood for centuries. It feels intuitive. The second idea, however, is where our familiar world begins to feel distant. It states that the speed of light in a vacuum, a number we call c, is the same for all observers, no matter how they are moving, or how the light source is moving. Let's pause with that for a moment, because it goes against our everyday experience with speed. Imagine you are standing beside a road, and a car passes at 60 miles per hour. If you are in another car, moving in the same direction at 50 miles per hour, the first car only seems to pull away from you at 10 miles per hour. We add and subtract speeds. It makes sense. Now, let us apply this to light. Picture a spaceship moving at half the speed of light. It turns on its headlights. We might expect to measure the speed of that light as the speed of the rocket plus the speed of light, 1.5 times c. But Einstein's second rule says no. You will measure the speed of that light to be exactly c. Not a bit more. And if the rocket flies away from you and turns on a rear-facing light, you will still measure its speed as exactly c. Even an astronaut inside the rocket will measure the light from her own headlights moving away from her at exactly c. This is the rule that changes our understanding of everything else. The speed of light is not relative, it is absolute. This has been confirmed by countless experiments. It is a fundamental truth of our universe. But how can this be? How can two people moving at different speeds measure the same beam of light and find the exact same velocity? For this to be true, something we consider unchanging must instead be flexible. If the speed of light is constant, then our very notions of space and time must be relative. They must stretch and shrink depending on your motion, to ensure that distance divided by time always equals c for light. To see this, we can use a thought experiment, the light clock. Imagine a clock made of two mirrors with a single photon of light bouncing between them. Each time the photon strikes a mirror, the clock ticks. If you are holding this clock, the photon travels straight up and down. A quiet, rhythmic tick. Now, let us place that clock on a fast-moving spaceship and watch it from the ground. As the clock moves horizontally, the photon, to get from one mirror to the other, must now travel along a diagonal path. This diagonal path is longer than the simple up and down path. And here is the key. According to Einstein's second rule, the speed of that photon is the same for us as it is for someone on the ship. So, if the photon must travel a longer distance, but its speed does not change, it must take more time to complete one tick. From our perspective on the ground, the moving clock is ticking slower. This isn't an illusion, it is a quiet, physical truth we now call time dilation. For the person on the spaceship, their clock is ticking perfectly normally. But if they were to look back at our clock on the ground, they would see our clock ticking slower, because from their perspective, we are the ones in motion. This is the first sign that time is not universal. If two observers cannot even agree on the length of a second, how can they agree on a universal now? The constancy of the speed of light makes time personal. Your experience of time depends on your motion. And this single consequence opens the door to the complete rethinking of simultaneity. We have seen that time itself is personal. We arrive now at the idea that sits at the center of this story, the relativity of simultaneity. It suggests that two events that happen at the same time for one person can happen at different times for another. The best way to see this is not with math, but with a picture. We are going to build a new kind of map, a spacetime diagram. Imagine a simple graph. The horizontal axis represents space, positions along a single line. The vertical axis represents time. An event is just a dot on this map, a specific place at a specific time. If you stand still, your position in space does not change, but time always moves forward. So your entire life on this diagram is a straight vertical line, rising through time. This is your world line. If you move, your world line tilts. Now, let's add light. Light travels at the fastest possible speed, and on these diagrams, its path is drawn as a line at a 45-degree angle. This is the ultimate speed limit. No physical object can have a world line more horizontal than this. From any single moment on our diagram, we can draw two of these 45-degree lines, creating an X shape. This is the light cone. It quietly divides the entire universe relative to that one event into three regions. The area inside the top cone is that event's future. Anything in this region can be reached from our starting point. The area inside the bottom cone is the past. Any event in this region could have caused our event. But what about the vast region outside the light cone? This is called elsewhere. An event in elsewhere is so far away in space and so close in time that even light has not had time to travel between you and it. You cannot affect it, and it cannot affect you. We have always assumed that this elsewhere could be neatly divided into past, present, and future. We thought of the present as a single horizontal line on this diagram, a slice across the whole universe. Einstein showed that this horizontal line is a personal perspective, not a universal truth. To see why, let's use his classic thought experiment. Imagine an observer, Priya, standing on a platform, exactly halfway between two trees. A very long, fast train moves past her. On that train is another observer, Raj, sitting in the exact middle of his car. Just as Raj passes Priya, lightning strikes both trees simultaneously. For Priya, standing still, the light from each strike travels the same distance to reach her eyes. The two flashes arrive at the exact same moment. Since she knows she is in the middle, she correctly concludes the lightning strikes happened at the same time. They were in her now. But now, let's see the world from Raj's perspective on the moving train. Remember the two rules. The laws of physics are the same, and the speed of light is the same. From his point of view, he is sitting still. The lightning strikes the front and back of his train car. But he is moving toward the light from the front strike, and away from the light from the rear strike. Because of this, the light from the front strike reaches him first. The light from the rear arrives a moment later. So what does Raj conclude? He knows he is in the middle of his car. He measures the speed of both flashes of light and finds them to be the exact same speed, c. Therefore, his only possible conclusion is that the lightning at the front of the train must have happened before the lightning at the rear of the train. Here is the quiet contradiction. Two observers, both making perfect logical sense of the world, arrive at two different truths. For Priya, the events were simultaneous. For Raj, the front strike happened first. They are both correct. There is no absolute answer. Simultaneity is relative. On a spacetime diagram, this disagreement becomes clear. Priya's now is a flat, horizontal line, containing both lightning strikes. But Raj's now, because he is in motion, is a tilted line. This tilted slice of reality intersects the front lightning strike at an earlier time and the rear lightning strike at a later time. This simple picture reveals a profound truth. There is no universal now. Every observer, based on their motion, slices up spacetime into their own unique present. This is a place where our intuition can feel lost, and that is understandable. We are challenging an idea that is built into our very perception of the world. So let us pause for a moment. What we've just seen is that the present moment is yours, and yours alone. It makes you wonder, if a civilization exists a million light years away, what does now even mean for them, relative to us? If this kind of calm exploration into the fabric of reality helps you see the world in a new way, consider liking the video and subscribing to the channel. Feel free to share your own thoughts or questions below. Once we accept that simultaneity is relative, the consequences ripple outwards, changing our entire picture of the cosmos. It leads to several profound realizations. First, the idea of a master clock quietly fades away. Priya on the platform is no more correct than Raj on the train. Both perspectives are equally valid. This means there is no true time to which we can all synchronize. Every frame of reference has its own time. We see this in practice, right now, above our heads. The Global Positioning System, or GPS, relies on this. Satellites orbit the Earth at high speed, and from our perspective, their clocks tick slightly slower due to special relativity. At the same time, because they are in weaker gravity, their clocks tick slightly faster due to general relativity. When combined, the clocks on GPS satellites run ahead of clocks on the ground by about 38 microseconds every day. If engineers did not correct for this, if they assumed a universal now, the system would accumulate errors of about 10 kilometers every day. Your phone's map would become lost. GPS works because it accepts that there is no master clock. This leads to a second consequence. Let's return to the elsewhere region on our spacetime diagram. For any event in your elsewhere, any event you are not causally connected to, there will be some observers who see it in their past, some who see it in their future, and one, you, who sees it as happening now. Imagine a civilization on Proxima Centauri b, about 4.2 light-years away. The question, what are they doing now, begins to lose its meaning. Because that world exists in our elsewhere, there is no single, objective fact about its present moment. An observer flying away from Earth might see their now slice through a time in Proxima b's past. An observer flying towards Earth might see their now slice through its future. There is no cosmic coordination. This forces us toward a stunning and humbling conclusion, an idea known as the block universe. If past, present, and future are not absolute, then perhaps the distinction itself is an illusion. Imagine the entire history of the universe, from its beginning to its end, as a single, four-dimensional block of spacetime. In this block, every event that has ever happened or ever will happen has its own fixed place. The dinosaurs are not gone, they are simply in a different part of spacetime. According to this view, our feeling of the flow of time is just our consciousness illuminating one slice of this block at a time, like a spotlight moving along a film. The entire film already exists. Your motion simply changes the angle of your slice through this 4D block. Priya and Raj were just slicing the same block of reality at two different angles. Both slices are equally valid ways of carving up the same underlying, four-dimensional existence. This is the ultimate consequence of letting go of a universal now. Reality may not be a series of fleeting moments, but a timeless, unified whole. So we return to where we began. Why can't the universe agree on now? We started with the comfortable, intuitive idea of a single river of time. We found that a single, unchangeable fact of our universe, the constant speed of light, requires that time itself be flexible and personal. We saw how motion causes time to slow, a real effect our technology must account for every day. And this led us to the final, quiet revelation, the relativity of simultaneity. Using a simple picture, we saw how two observers can fundamentally disagree on what is happening at the same time. Priya saw two lightning strikes happen at once. Raj saw one happen before the other. And the universe tells us that they are both right. The universe does not have a master clock, because every observer carries their own. It does not have a shared now, because each of us slices the fabric of spacetime in our own unique way. Your now is not a shared cosmic moment, but a private cross-section of a much larger, four-dimensional reality. The feeling of a universal present is a local illusion, born from the fact that we move so slowly through the cosmos. We are left with a picture of the universe as a vast, four-dimensional block, where all of time exists at once. Our consciousness travels through it, illuminating a slice we call the present. But our slice is just one of infinitely many. Your present is another's past, your past is another's future. This new map of reality, of course, leaves us with quiet, profound questions. If the future exists in the same way as the past, what does that mean for our journey through it? Physics has shown us the shape of this block, but it has not yet told us what it means to be the consciousness that moves across it. The distinction between past, present, and future may be an illusion, but it is a powerful one, and perhaps the most deeply human one of all. If this journey through space-time has helped you see the world in a different way, consider liking this video and subscribing for more explorations into the quiet, deep ideas of the cosmos. In our next video, we will travel to a place where time itself seems to end, the heart of a black hole. There is a sense, intuitive and deeply felt, that this moment is something we share. That as you watch this, and as I speak, we exist in a common slice of time called now. It feels absolute, a fundamental feature of the world. But the physical universe operates on a different principle. The shared moment we feel is an illusion, a persistent and useful one, but an illusion nonetheless. Your now is a private experience, and there is no single, universal present that stretches across the cosmos. This is not a philosophical proposition, it is a consequence of the laws of physics. And it reveals a universe that has never agreed on now. For much of human history, our model of time was straightforward. It was a great, cosmic clock. This idea was given its most powerful form by Sir Isaac Newton. In his Principia Mathematica, he described a universe that would be the foundation of science for more than 2 centuries. In Newton's universe, time was absolute. He wrote that it, of itself, and from its own nature, flows equably without relation to anything external. It was an invisible river, flowing at the same constant rate for everything, everywhere. For someone on Earth, for a traveler on a hypothetical distant world, Newton's clock would tick in perfect unison. A single, now, existed for the entire cosmos, an instantaneous moment that connected all things. This view is aligned with our direct experience. If I snap my fingers, that event feels as if it happens for the entire universe at that one instant. My now feels like your now. If we synchronize watches, we expect them to remain synchronized. Our lives are structured around this assumption. We arrange meetings, launch spacecraft, and mark the new year as if now is a shared global, and even cosmic, event. On the human scale, this model works. The differences are so small they're unnoticeable. We live on a stage where the background seems fixed, and the clock appears to tick the same for every actor. For centuries, this framework was perfect. It allowed for the prediction of planetary motion and the construction of a physics that seemed complete. The universe was an orderly, predictable machine, and time was its master beat. But a problem began to emerge from within this mechanical certainty. An observation that did not fit. It came not from a planet or a clock, but from a beam of light. And it would be this constant that would ultimately dismantle the universal clock. The first indication that the Newtonian foundation was incomplete came from the work of James Clerk Maxwell. In the 1860s, he unified electricity and magnetism into a single theory of electromagnetism. His equations were a monumental achievement, but they contained a strange prediction. They predicted that light was an electromagnetic wave that traveled at a specific speed, c. approximately 299,792 kilometers per second. The strange part was that the equations did not specify what this speed was relative to. The speed of a light beam wasn't its own speed plus the speed of its source. It was simply c. Always. This was in direct conflict with the established principles of motion. If a train passes a platform at 100 km per hour, and a person on the train throws a ball forward at 20 km per hour, an observer on the platform sees the ball moving at 120 km per hour. The speeds are additive. This is Galilean relativity, the bedrock of intuitive physics. But if you replace the ball with a beam of light, the rules change. A person on the 100 km per hour train turns on a flashlight. The observer on the platform measures the speed of that light. The result is not c plus 100 km per hour. The result is simply c. The person on the train also measures the light's speed and gets the same result, c. It does not matter how fast the observer or the source is moving. Everyone, in any state of uniform motion, measures the exact same speed for light. This was a profound paradox. Physicists in the late 19th century proposed explanations, including a hypothetical medium called the luminiferous ether, that was thought to fill all of space. But experiments designed to detect our motion through this ether, most famously the Michelson-Morley experiment, found nothing. The ether did not seem to exist. The universe was presenting a choice. Either the fundamental principles of motion were wrong, or our concepts of space and time themselves were flawed. The constant speed of light was a paradox at the heart of physics. The resolution would come from a patent clerk in Bern, who decided to accept the paradox as a statement of fact. In 1905, his Annus Mirabilis, or Miracle Year, Albert Einstein published his special theory of relativity. He did not attempt to explain why the speed of light was constant. He accepted it as a fundamental principle of the universe. He began with two postulates. First, the principle of relativity. The laws of physics are the same for all observers in uniform motion. An experiment inside a smoothly moving, windowless container cannot tell you if you are moving or standing still. Second, the constancy of the speed of light. The speed of light in a vacuum, c, is the same for all observers, regardless of their motion. Einstein's work was to follow the logical consequences of these two ideas being true simultaneously. If the speed of light is absolute, then something else must be relative. If the cosmic speed limit is fixed, then our measurements of distance and time must change depending on our motion. To make the physics consistent, Newton's idea of absolute space and time had to be abandoned. Einstein showed that space and time were interwoven into a single, flexible entity, spacetime. And this spacetime could stretch and contract. His theory predicted that for a moving observer, time itself passes more slowly relative to a stationary observer. This is time dilation. If a person traveled in a spaceship at a significant fraction of light speed, their clock would tick more slowly than a clock on Earth. Upon their return, they would have aged less. This is not a perceptual trick, it is a physical reality. The faster you move through space, the slower you move through time. The theory also predicted length contraction, that an object in motion shortens in its direction of travel, relative to the observer. These were radical ideas. They replaced the predictable, clockwork universe of Newton with a strange, elastic reality. But the most profound consequence was not just that time could slow down. It was that the very concept of now depended on your point of view. This leads to the core of the issue, the concept that explains why the universe cannot agree on now. It is called the relativity of simultaneity. Einstein demonstrated that two events happening at the same time for one observer may happen at different times for another. To understand this, he used a thought experiment involving a train and two lightning bolts. Imagine a long, straight track. An observer, Anna, stands on a platform, exactly at the midpoint between 2 points on the track, A and B at the same moment. Two lightning bolts strike the track. One at point A and one at point B. Light from both strikes travels toward Anna. Because she is in the middle and the speed of light is constant, the two flashes reach her eyes at the exact same time. She sees them simultaneously. Anna correctly concludes that because she is at the midpoint and saw the flashes at the same time, the strikes themselves must have happened at the same time. For her, the events were simultaneous. Now, we introduce a second observer. Ben is on a very fast train moving along the track from A towards B at the exact instant the lightning strikes. Ben, seated in the middle of his train car, is passing directly in front of Anna. The strikes leave scorch marks on the track and on the very front and back of his train car. What does Ben see? Einstein's second postulate is key. The speed of light is constant for everyone. As the light from the two strikes travels toward Ben, he himself is moving. He is moving toward the flash coming from point B at the front, and away from the flash coming from point A at the back. Because he is moving toward the source of the front flash, that light has a shorter distance to travel to reach him. The light from the rear flash must travel a longer distance to catch up to his moving position. The result is that Ben will see the flash of light from the front of the train before he sees the flash of light from the back. Ben is also a careful observer. He knows he is in the middle of his train car. He knows the speed of light is constant. He observed the light from the front arrive first. He must therefore conclude that the lightning strike at the front of the train happened before the strike at the back. For Ben, the events were not simultaneous. The question then is, who is right? Anna, who says the events were simultaneous? Or Ben, who says the front event happened first? Einstein's answer was that both are right. There is no single, objective truth of the matter. Simultaneity is not an absolute property of the universe. It is relative to the observer's motion. The question, did these events happen at the same time, is incomplete. It must be followed by, according to whom. If different observers cannot agree on whether two distant events happened at the same time, then the idea of a universal, now, is gone. My now is the collection of all events I determine to be happening at this instant. If we are sitting still relative to each other, our nows are almost identical. But if you are in motion relative to me, our definitions of now are different. Your present moment is a different set of events than mine. To visualize this, physicists sometimes use the analogy of the block universe. Imagine spacetime, the four dimensions of three spatial dimensions plus time, as a single, solid block. This block contains every event that has ever happened or ever will, from the Big Bang to the ultimate end of the cosmos. Your birth, the age of dinosaurs, this moment, and your entire future all exist as coordinates within this block. In this model, an observer's present moment is not a single point but a three-dimensional slice of the four-dimensional block. It is a cross-section of the entire universe that, from one particular perspective, is happening now. If you are standing still, your slice of now cuts straight across the block. But the relativity of simultaneity shows that if I am moving relative to you, my slice of now is cut through the block at an angle. My angled slice will contain events that, on your straight slice, are in the past. It will also contain events that are in your future. An event on a distant galaxy that exists in my present moment could be an event that, from your perspective, happened 1,000 years ago. Another distant event in my present could be in your future. The disagreement grows with distance and relative speed. For two people walking past each other, the tilt is imperceptible. But for an observer on Earth and a hypothetical craft in another galaxy moving at high velocity, their nows could be tilted by millions of years. There is no correct slice. The universe does not have a preferred now. There is only the complete, four-dimensional block of spacetime. Each of us, on our own trajectory through it, experiences our own sequence of these slices. This can seem to imply that reality is disordered. If my future can be in someone else's past, does that mean an effect can happen before its cause? The answer is no. Einstein's universe has a rule more fundamental than simultaneity, the law of causality, enforced by the speed of light. While observers can disagree on the timing of some events, they will never disagree on the order of events that are causally connected. The universe has a structure that preserves the chain of cause and effect, known as the light cone. Imagine an event, a snap of the fingers. The influence of that snap, the light and sound, expands outwards in a sphere. On a spacetime diagram, this expanding influence forms a cone shape, the future light cone. It contains all points in spacetime that can be affected by the snap. Anything outside that cone cannot be affected, because a signal would have to travel faster than light to reach it. There is also a past light cone, which contains all events that could have possibly influenced the snap. Here is the absolute rule. For any two events where one is in the other's light cone, a cause and its effect, all observers will agree on their chronological order. Everyone will agree the match was lit before the fire started. The order of these time-like, separated events is absolute. Disagreement only happens for events that are outside each other's light cones, called space-like, separated events. The two lightning strikes in the thought experiment were space-like separated. Because of the distance between them, neither could have caused the other. For these events, their ordering is relative. Some observers see A happen before B, others see B happen before A, still others see them happen at the same time. But because they cannot affect each other, the ordering does not violate causality. The universe does not require a universal now to maintain order. It relies on a more robust system, a universal agreement on cause and effect. If the block universe model is accurate, and the past, present, and future all exist within it, then why do we experience time as a flow? Why is there a powerful sensation of moments arriving, becoming present, and then receding into the past? This is one of the deeper questions in physics, and there are several parts to the answer. One part is physical, and relates to entropy. The second law of thermodynamics states that the total disorder, or entropy, in a closed system tends to increase over time. The universe began in a very low entropy state at the Big Bang and has been expanding and becoming more disordered ever since. This one-way increase in disorder gives time a direction, an arrow. We remember the past because it was a more ordered state. The future is not remembered because it is a state of higher probability and less order. The flow we feel may be our perception of this constant increase in entropy. Another part of the answer is neurological. Our brains are machines that construct a narrative from sensory information. Memory is asymmetric. We accumulate records of the past, but not the future. This process of constantly updating our model of reality based on new information creates a powerful psychological experience of passage. The present is the leading edge of our awareness as it processes the world. The feeling of time's flow, then, is a product of both a fundamental physical process and the way our brains interpret reality. We are entities existing within the block universe, but our consciousness illuminates it one slice at a time, creating the story of a journey. This may all seem like abstract theory, but the relativity of time is a measurable reality that modern technology depends on. The most prominent example is the Global Positioning System, or GPS. The GPS network is a collection of satellites orbiting Earth at about 14,000 kilometers per hour. A receiver on the ground determines its position by triangulating incredibly precise timing signals from several of these satellites. Those satellites are subject to the laws of relativity. First, because of their high speed relative to the ground, their internal atomic clocks experience time dilation. From our perspective, their clocks tick slower by about 7 microseconds each day. Second, the satellites are in a weaker gravitational field. Einstein's general theory of relativity predicts that time moves faster in weaker gravity. This effect causes the satellite clocks to tick faster than ours by about 45 microseconds each day. The combined result is that the clocks on GPS satellites run ahead of clocks on Earth by about 38 microseconds every day. This small amount, 38 millionths of a second, is critical. If the engineers who designed GPS had used a Newtonian model of absolute time, the system would be useless. The timing discrepancy would accumulate, causing positioning errors of roughly 10 kilometers every single day. To function, the GPS system is built to constantly correct for the fact that time is running at a different rate in orbit than it is on the ground. Every time you use a map on your phone, you are relying on a technology that confirms time is not absolute. The now on the satellite is not the same as the now down here. We began with the intuitive model of a universal clock, a single beat for the entire cosmos. We saw how the constant speed of light revealed this to be incomplete. We followed Einstein to see that simultaneity itself is a matter of perspective. Our shared now is an illusion, and reality is more like a four-dimensional block of spacetime, through which each of us carves our own unique slice of the present. Yet, there is still order. The universe does not have a universal now, but it is governed by a universal law of causality. The order of cause and effect is absolute, preserved for all observers by the cosmic speed limit. This view of reality can be unsettling. It changes our position from actors in a play that unfolds moment by moment, to readers of a story that is, in a sense, already written. How this idea of a personal now within a block universe feels is a question worth considering. In the end, that the universe doesn't agree on now does not make it less magnificent. It makes it more intricate. It suggests that our personal experience of time, that intimate feeling of the present, is uniquely our own. We may not share the same cosmic instant, but we are all embedded in the same four-dimensional structure. We are all bound by the same unbreakable laws. The universe may not agree on now, but it does agree on the story, the interconnected story of all things, and we are all a part of it. We move through our lives on what feels like a shared frontier, a single, moving line we call now. We believe that as you watch this, we are in this moment together. But what if the now you inhabit is a private world, a story told only to you? A story of a reality that is already in the past. A ghost. A memory. This isn't a philosophical riddle. It's a quiet truth of our biology. The seamless, flowing present you experience is a carefully constructed illusion, a narrative your mind assembles after the events have already occurred. And what is truly remarkable is that this story is unique. Your now is not my now. In a world of billions, billions of different present moments unfold, all happening at once, yet all slightly out of sync. We assume now is a universal territory. But the truth is quietly strange. Your brain lives in its own personal present, a reality stitched together from delayed signals. This is a journey through how your consciousness, locked in the dark, silent theater of the skull, builds a world that feels immediate and real, even though it's a completely personalized timeline. This is the story of why the universe, and our brains, seem to have never agreed on now. Our journey begins not by looking to the stars, but inward, by exploring a fundamental assumption we all make: that time is something we perceive. We think of it like a sense. We see light, we hear sound, and we experience time. But that's not how it works. Time is not a signal from the outside world. There is no hidden organ in the body, no special receptor for sensing the flow of moments. Instead, time is something the brain constructs. It is an internal creation, a piece of cognitive software that runs constantly, allowing us to make sense of the world. We have all experienced this. 5 minutes waiting for something important can stretch into an agony. Yet 5 hours spent lost in a passion, a state of flow, can vanish. The clock on the wall moves with an objective, relentless rhythm. But our internal experience, our personal time, stretches and compresses. It's a quiet paradox we all live with. The reason is that our experience of time isn't a measurement of the external world. It's a reflection of our internal one. Your brain is not a passive receiver of time, it is its creator. It actively generates the very sensation of time passing, weaving it from 3 threads: attention, memory, and emotion. Attention acts as a lens for our perception of time. When we are bored or anxious, our brain dedicates immense resources to monitoring the slow crawl of moments. We are paying attention to time itself, making it feel unbearably long. But when we are deeply engaged, our attention is focused elsewhere. We dedicate no energy to tracking time, so our brain simply doesn't register its passage. Time seems to disappear because, for our conscious mind, it has. Then there is memory. Our sense of time is deeply connected to how our brain stores information. A day filled with new experiences, new sights, new challenges, feels incredibly long in retrospect. It's because the brain had to write down a massive amount of new information. Conversely, a routine day feels like it passes in an instant. The brain, being efficient, doesn't need to write down much new data for familiar events. As the neuroscientist David Eagleman describes, the more familiar the world becomes, the less information your brain writes down, and the more quickly time seems to pass. This is why childhood summers seem to last forever. As a child, almost everything is a new experience, a flood of novel information stretching our memory of that time. As we get older, our world becomes more familiar, and our timeline feels compressed. Finally, there is emotion. Your emotional state can change the tick rate of your internal clock. In moments of intense fear, like a car accident, people often report that time seemed to slow down. This isn't because time changed, but because the brain went into overdrive. The amygdala, its threat detection center, begins recording memories with an incredible level of detail. When we play that memory back, it contains so much more data than a normal moment that it feels stretched out, as if it lasted longer. These 3 elements are always interacting, creating a unique temporal world for each of us. Your personal present is not a fixed point, but a dynamic and entirely subjective construction. The clock on the wall may govern our schedules, but it's the clock in the mind that governs reality. And that clock runs on a time that is yours, and yours alone. So, we've established that our sense of now is a personal creation. But here, the story deepens. The most remarkable part isn't just that your now is unique. It's that it isn't happening now at all. Your conscious awareness of the world is lagging behind the world itself. At this very moment, you are living in the past. The delay is small, estimated to be somewhere between 80 milliseconds and half a second, depending on the sense. But it is there. For example, some studies suggest a visual signal can take hundreds of milliseconds to be fully processed and enter our awareness. A famous and much debated series of experiments by neuroscientist Benjamin Libet in the 1980s suggested that brain activity to initiate an action, like moving a finger, begins about half a second before the person consciously decides to act. The body prepares to move before the mind is even aware of the intention. We don't decide and then act. We become aware of a decision our brain has already set in motion. This delay is a consequence of biology. The brain is encased in bone, with no direct access to the world. It only receives electrical signals, delivered by nerves at different speeds. A signal from your eyes travels faster than one from your toes. A sound might arrive before a sight. If your brain presented this information as it arrived, reality would be a chaotic, disjointed mess. To solve this, the brain has become a master editor. It waits. It collects all the sensory data arriving within a small window of time and holds it. Only when it has all the relevant pieces does it perform an incredible act of post-production, synchronizing these disparate signals into a single, coherent story. Then, it presents that story to your conscious mind. The now you experience is this final, edited version. It's not a live broadcast, it's a tape-delayed special. Your brain even performs a clever trick, retroactively dating the experience to the moment the first signal arrived, creating the illusion that you experienced it all in real time. This has led to a quiet revolution in neuroscience. The idea that the brain is a prediction machine. For a long time, we saw the brain as a reactive organ. But a new theory, predictive processing, flips this on its head. It argues that the brain isn't passively waiting for information. It is constantly, actively generating a model of the world. A full-scale simulation, based on all your past experiences. The job of your senses, then, is not to build the world from scratch. That would be incredibly inefficient. Instead, the senses are primarily error checkers. The data flowing into your brain is compared against the predictions it's already making. If the incoming data matches the prediction, if the chair feels as your brain predicted, the signal is essentially cancelled out. But if there's a mismatch, an unexpected sound, a sudden movement, that creates a prediction error. That error is the newsworthy information that gets fast-tracked to your conscious attention to update the model. This is why optical illusions work. They exploit the predictive models your brain uses, making a top-down prediction so strong it can override the bottom-up sensory data. This entire process, data collection, synchronization, prediction, and updating, takes time. That is the delay. The conscious experience of now is the moment you become aware of the brain's updated model of the world. You aren't perceiving the world. You're perceiving your brain's best guess about it, just a fraction of a second late. At this point, you might feel that this system is a flaw, that we are detached from true reality. But this couldn't be further from the truth. This system of delay and prediction is one of the most brilliant features of the brain, a survival mechanism shaped by deep time and chance. The reason your brain works this way is not to deceive you, but to keep you alive. Think of the sheer amount of information bombarding your senses. It's been estimated that the unconscious mind processes something like 11 million bits of information per second, while our conscious mind handles a paltry 50. If you tried to consciously process all of that raw data in real time, the experience would be an overwhelming storm of static. You wouldn't be able to form a single, coherent thought. The brain's editing and prediction process is a radical act of data compression. It filters the noise to give you only the most critical, actionable information. It prioritizes a stable, coherent, and useful story about the world over a perfectly accurate, real-time data stream. A coherent story is something you can act upon. A blizzard of raw data is not. This predictive ability is also about conserving energy and increasing reaction speed. By anticipating what's likely to happen, the brain prepares your body to act. Consider a baseball player facing a fastball. The ball travels from the pitcher to the plate in about 400 milliseconds. We know it takes the brain a significant portion of that time just to process the visual data and command the muscles to move. If the batter waited to consciously see the ball, decide to swing, and then act, the ball would be in the catcher's glove. The only way to hit the ball is through prediction. Based on the pitcher's motion, the batter's brain generates a prediction about where the ball will be. The swing isn't a reaction to where the ball is. It's an interception aimed at where the ball is going to be. They are swinging at a ghost, a predicted future location. This is active inference in its purest form, an echo of the adaptations seen in the earliest predators calculating the path of their prey. The feeling of now is the feeling of the brain's story being told. Consciousness creates the illusion of a smooth, continuous flow because a gappy, disjointed story is not useful for a creature trying to navigate a complex world. We need a continuous narrative to understand cause and effect, to plan, and to form a stable sense of self. This process isn't a bug, it's the very feature that allows you to have a stable reality. Your brain acts as a masterful storyteller, taking the complex, noisy data from the world and crafting it into a simple, elegant narrative you can live in. It's a survival mechanism disguised as a simple sensation, a life-saving tool we mistake for the ticking of a clock. We have journeyed deep into the inner world of the brain, to find that our personal now is a private timeline. This idea feels radical, but what is truly remarkable is that this strange, subjective nature of time finds an echo in the fundamental laws of the universe itself. Long before neuroscientists began this work, physicists were arriving at a similar, mind-bending conclusion. There is no single, universal, now. This is one of the revelations of Albert Einstein's theory of relativity. Before Einstein, the universe was imagined to run on a single, master clock. Isaac Newton saw a world where time flowed at a constant rate for everyone, everywhere. Now was absolute. This fits our intuition, and it's wrong. Einstein showed that time is not absolute. It is relative. The rate at which time passes depends on your motion and your proximity to a strong gravitational field. This isn't a trick of perception, it's a physical reality. The clocks on GPS satellites have to be constantly adjusted for these effects, or the entire system would fail. What this means for now is profound. Imagine you are standing in the middle of a moving train car. As you pass a friend on a platform, lightning strikes the front and back of the train at the same time. From your perspective, the light from both strikes travels an equal distance, so you see them happen simultaneously. A single now, but your friend on the platform sees something different. Because the train is moving, the light from the back of the train has farther to travel to reach them than the light from the front. They will be certain that the lightning struck the front of the train before it struck the back. It was not a simultaneous event. So who is right? You, who saw the strikes happen together? Or your friend, who saw them happen at different times? According to Einstein, you both are. There is no absolute answer. Now is not a universal plane that cuts across the cosmos. Each observer has their own personal slice of now, determined by their motion. This physical reality is a strange and beautiful mirror to our neurological one. Physics tells us that different observers have different nows. And long before Einstein, our brains already embodied this principle. Your consciousness creates a now that's uniquely yours. The universe doesn't force everyone into the same moment. It allows each observer, each conscious mind, to construct their own. The deep strangeness of our inner world is echoed in the deep strangeness of the outer world. Both tell us the same thing. The solid, reliable present we take for granted is the most personal and private experience you can have. So where does this journey leave us? We've learned that the now you inhabit is a ghost, a story woven from memory, attention, and emotion. We've learned that this subjectivity isn't just a biological quirk, but a fundamental principle of the universe. The implications of this are vast. First, it forces us to confront the profoundly subjective nature of experience. We walk around assuming we all share the same world at the same time. But we don't. Every single conscious being is living in a slightly different version of reality. Our realities are similar enough for communication, but they are not identical. We are, in a very real sense, islands of awareness. This understanding can cultivate a profound empathy. When you realize another person's perception of an event is being constructed by a different brain with a different history, it becomes easier to understand why different perspectives arise. Second, this new perspective offers a powerful tool. If our experience of time is a malleable construction, then we have some power to shape it. Do you feel like the years are passing in a blur? The science we've discussed offers a clear prescription. Seek novelty. Break your routines. Learn a new skill. By feeding your brain new and complex information, you force it to write down more memories, making time feel longer in retrospect. The way to stretch your life is not to add more years, but to add more new experiences to the years you have. Conversely, to make a difficult task feel shorter, the key is to find a state of flow, immersing yourself so completely that your brain stops tracking the passage of time. You become a co-director of your own reality, consciously manipulating the very inputs your brain uses to build its timeline. Finally, accepting the constructed nature of now can be a form of liberation. The deepest insight from this journey is that your personal, subjective experience of time is valid. The universe doesn't demand that we all experience now in the same way. Perhaps the goal isn't to perfectly synchronize our internal clock with the external one. Perhaps the goal is to understand our internal clock, to learn its rhythms and appreciate its quirks, and to use that understanding to build a richer, more meaningful experience of the time we have. The present moment is not a point you arrive at. It's a reality you create. The journey into our own perception is one of the great frontiers of science. The questions we've explored today are just the beginning, and every new discovery reveals another layer of wonder. If this exploration has sparked your curiosity, we hope you'll join us for future journeys into these kinds of mind-bending topics, from the nature of consciousness to the future of intelligence. There's a vast universe to explore, both outside of us and within us. And it brings to mind a question. Can you think of a time when your personal sense of time felt completely distorted? A moment that seemed to last forever, or a day that vanished in a flash? Sharing these stories in the comments is a powerful reminder that while each of our nows is unique, the strange and wonderful ways our brains construct them is a universal human trait. We began with a simple premise: you're living in the past. We've seen how your brain, like an editor, collects and synchronizes sensory data, creating a coherent story only after the events have occurred. We've discovered that this process is radically predictive, with your brain constantly modeling the world and using your senses to check for errors. This entire, elegant operation is what you experience as the present. It's a profound shift in perspective. To realize that now is not a universal constant, but a personal, biological construct. Your consciousness isn't a window looking out onto the world. It's a canvas on which your brain paints its best guess of the world. And it's always working from slightly old sketches. But instead of feeling detached, perhaps this should make us feel more connected to our own experience. Our life is not just something that happens to us. It is something we are actively creating, moment by moment, prediction by prediction. So, the next time you experience a moment, take a second to appreciate the incredible artistry behind it. The feeling of the sun on your skin, the sound of a voice. Remember that this experience is not a direct recording. It is a masterpiece of neurological storytelling. A story crafted exclusively for you by the most complex object in the known universe, your brain. You aren't just living in this moment. You are creating it.